Hi, Sir Perry. Wala akong sound.
Ako yung walang sound. Naka-unmute ka.
Nako. Dinig niyo ako?
Yes, sir.
Okay. Eric, sound check.
Sound check.
Mute ko muna na sarili.
Okay, hello. Kompleto na ba tayo? So I see Eric, Ma'am V.
Hello, narinig niyo ka?
Yes.
Okay.
Okay, very good. Si Perry nandyan na. We have visitors from all around. Reina is here as well. Teka.
Hello.
Sound check, Reina. Hi, kumusta?
Hi naman.
So,
Ayan. Naka-mute kanina eh. Okay. Okay na.
ayun. Okay, sige. So, ganito na lang ang gagawin kasi this is the first. Kaya tayo nag-start ng 3:45-ish kasi 4 o'clock talaga dapat ang start, but we wanted to make sure that everything is working fine. And I'm glad to see all the examiners and the readers here. Nadidinig naman lahat, hopefully. Okay, excellent. So we'll officially start at 4 o'clock. So mag-hi, hello muna tayo. It looks like we have, so Tram is with us. So hi Tram, kumusta? Tram is presently quarantined in Trieste. We also have Bill here, who's still awake at 3:52 a.m. in Chapel Hill, North Carolina. So thank you Odin, Jess. Yeah, so sana okay naman kayong lahat. Kumusta naman tayong lahat?
Good.
Okay, sige.
Mukhang tumaba lahat
Dapat lang COVID-19 ay yung 19 daw na yun, 19 pounds yun. Ang tanong ay less ba or greater than 19? May nakakaalam ba kung ilan pwede ang ma-admit dito sa Zoom meeting? May max ba tayo?
Well, kung sakali may max naman, may naka-live stream na tayo sa YouTube. Kaka-post ko lang ng link.
Okay.
So pwedeng yung iba, so hindi masyadong crowded yung Zoom, sa YouTube na muna manood.
I-send ko para ma-advertise ko.
I think 200 or something like that.
Okay, sige, 200. So naka-live on YouTube na. May YouTube link, Reg.
Yeah. Kaka-post ko lang. Lalagay ko sa chat.
Sige.
Ayun.
Hindi clickable or copyable ang link sa chat.
Oo nga.
Oo nga. Paano gagawin to?
Hayaan mo na. Gawin mo daw public yung post mo kasi naka-private yung post mo.
Sige. Edit post.
May 6 minutes pa naman tayo. Buti naman gumagana lahat. Parang mas kinakabahan ako kaysa kay Reggie. Parang ako yung magde-defend. Hindi naman ako dapat yung magde-defend. Teka, share ko lang to.
Merienda lang muna ako, ha?
Sige.
Kailangan mag-mute muna ako. Then mag-prepare lang din ako.
Tinatry ko lang yung mga buttons dito ha. Kung ano tong mga to.
Ma'am V, pwede ba kitang
Yes.
i-request na mag-moderate?
Ay, nasan pala yung sign sheet nito?
Nandun sa email. So, isi-send na lang natin kasi syempre wala namang precedent dito. So, we'll make up the rules as we go. So, I presume na parang same lang as before, kaso nga online lang. So, after the defense and after the Q&A, baka mag-convene tayong 5 to talk about whether to pass him or not. Tapos, tapos then I'll forward the email which includes all of the forms. Tapos siguro lalagay tayo ng mga e-signatures na lang natin. So yun yung presumption ko, although wala namang specific instructions from the College of Science. So for now, siguro ma'am, kung pwede po, as soon as we start officially at 4 o'clock, I'll say a little bit, then I'll pass the floor on to you, ma'am.
Okay, sige. Okay.
Tapos, so for a Q&A, para hindi magulo kasi I'm pretty sure, so now we have 26 participants and it's growing. Sa chat na lang po, tapos kayo na lang po mag-screen kung, may repeated question na, ganyan. Baka parang pwedeng i-summarize na lang sila or i-condense na lang yung mga questions na overlapping naman yung content. Pero baka
Okay,
pwedeng para hindi magsasalita lahat ng tao, doon na lang sa chat siguro. Chat feature ng Zoom. So si Dr. Villagonzalo ang magiging moderator natin for this event.
May chat. Paano ba ito?
May chat, pwede pa unmute ako. Hindi, pero yung examiners dapat hindi naka-unmute kasi the examiners should be able to interrupt anytime. So
Okay.
kung gusto niyo mag-interrupt, if there's anything unclear that does not or cannot wait till the end, feel free to ask questions. So again, this is a precedent setting in more ways than one. So malabo din to for me. I mean, malabo in a good way as well. Pero it'll be
Sino ang may control ng mute?
I think
Si Reggie?
Ginawa kong co-hosts lahat ng panel.
Yeah.
Tapos you have the power to unmute.
Okay, sige.
okay. So nandun na ba yung YouTube link, Reggie?
Yes, nasa post ko. Naka-public na din public na din siya. So pwede siyang i-share kung
Nakikita ko dito live on YouTube.
Yeah.
yes, ma'am.
Na-miss
I
ko
think-
tuloy ang theory.
Oo nga eh. Na-miss ko NIP.
Hi, sir.
Ay, Reggie, na-miss ko tuloy ang theory. Sino ba yung mag-a-admit dito? Nakalagay dito, admit, ano yun? Si waiting room, ano ba to?
Kahit sino
yes,
sa
sir.
atin.
Kahit sino sa
I
atin
think
pwede mag-admit? Sino bang mag-a-admit dito?
Tulungan daw si Dr. Isguera, hindi niya ma-unmute.
May class.
Ay, Sir Penry, may
Okay.
Ayun.
Dinig niyo na ako, no?
Oo.
Okay,
Yan.
okay.
Thank you.
Pero ba't
Yan,
parang
pwedeng
electronic ang boses mo?
May background. Oo.
Baka yung aircon. Hindi, baka mas useful tanggalin ko to.
Bakit may
Nag-improve ba?
Ba't may mga ads itong ano?
Ba't may ad to?
Oo.
Di ko sure.
Ads? Talaga? Wala akong makita nga.
Dun sa chat meron.
Meron.
Dapat ginamit mo yung
Galing to.
Zoom na yung UP, yung @up.edu kasi ano yon, licensed na Zoom yon.
Yes, ma'am. Ito naman po yung gamit ko.
Hindi, si Dr. Galapon.
Ganun ba?
Ah,
Hindi. Yun ako naka at UP ako.
Wala akong advertisement na nakikita.
Oo. Ako rin.
Oh, okay.
Ako rin wala.
Baka sa akin lang kasi hindi yung UP yung ginagamit ko.
Hindi, ako meron
Oo.
din. Meron din akong ads.
O, libre kasi yung ginagamit mo. Ay, naku, ba't tayo na lang? Ba't
Ayan.
nabawasan tayo?
Hindi kasi hindi may panel, may view yung grid video.
Ay.
Makita lahat. Ayan.
Okay ito ah.
Okay, so we can officially start. It's 4 o'clock. Tama ba?
Yes,
yes,
401.
401.
So,
Pwede po mag-admit, ano?
admit lang kayo ng admit. So let's officially start.
Okay.
So it's my distinct pleasure. It's my distinct pleasure to welcome everyone to NIP's first or inaugural online PhD defense. It is also my distinct pleasure to introduce our speaker today. So this is groundbreaking in more ways than one. Like I said, it's the first online PhD defense of NIP and probably of the College of Science as well. And with any luck, our speaker will, after this, will also share the distinct honor of being the first, possibly, PhD in gravitational physics in the history of the country, in the entire throughout the history of the country. So, as the first PhD in gravitational physics, Reggie potentially will become heir to a proud tradition that traces its roots all the way to the origins of modern science, from Galileo to Newton, all the way to Einstein, and finally we have our own line here in the Philippines. So welcome everyone. I hope this is going to be educational and fun for everyone in the audience at the moment. Of course, we would have wanted this defense to be held on a more opportune time, but fate has not been very kind to us. So we have to make do with what we have, and so so let's make the best of it. So without further ado, I will pass the floor to our moderator, one of the readers, one of Reggie's readers for this defense, Dr. Villa Gonzalo.
Okay, so let me just remind Reggie that the presentation and the open forum is for 1 hour. Okay, the 1 hour already includes the presentation is for 1 hour. Sorry, for 1 hour.
Yeah, thanks.
The panel members are Dr. Eric Galapon, Dr. Reynabel Reyes, Dr. Jose Perico Esguera, and of course the advisor, Dr. Ian Vega, and yours truly as the reader. So also Dr. Galapon is also the other reader. Okay, so we are here this afternoon to hear the dissertation defense of Reginald Christian Bernardo. So please, you can have the floor.
So thank you, Ma'am V, for the introduction, and thank you, panel members, for granting me this opportunity, and thank you everyone for attending my PhD defense. This is of course a very important event in my life. If you want, you could regard this basically as the final exam during the finals week for a PhD student. So so let's do this. The title of my talk is Compact Objects, Cosmologies, and Gravitational Perturbations in Scalar Tensor Theories of Gravity, the same title as my thesis. And of course, I'm Reggie Bernardo. So yeah, I prepared a roughly 1 hour talk with the following outline. I'm going to give a very brief introduction to the theory of relativity. And then I give a short talk on scalar tensor theories of gravity, basically the topic of my thesis. I talk about Horndeski theory and a very important gravitational wave astronomy constraint today, GW 17817. And then I talk about kinetic gravity braiding, which is basically the scalar tensor theory topic of my PhD thesis. And yeah, as the title of my thesis suggests, the main topics of my thesis are on compact objects, cosmologies, and gravitational perturbation. So I'll talk about that later, and then after doing that, I'll summarize everything, get to the big picture, what is it that basically I have done. So things start with the theory of relativity. Shown here is, of course, perhaps one of the most famous equations today, E is equal to mc squared, which means basically that mass can be converted to energy. Energy could, on the other hand, be converted into mass. But then as we know that it is the mass of objects that sources the gravitational field. You have a massive object, then things are going to orbit around it. So then the gravity picture emerging, starting from this idea, is the general theory of relativity. So, so now it is more generally that the energy is the source of the gravitational field, and that's the content of this new theory. So to be able to affect everything in it, basically gravity affecting everything, the gravity is treated as the metric field in the general theory of relativity. So the metrics, basically, you could think of that as the curvature of the space-time. So we are all moving in this space-time, so that means that our motions are all affected by gravity. Yeah, and the main equation of the general theory of relativity is shown here. So that there in the box, the Einstein equation. So that so let me just read that. GAB equals 8 pi g over c to the fourth times TAB, where capital G is the Newton's gravitational constant, and small c is the speed of light in vacuum. An object like this with subscripts, this capital G, then subscript AB, is called a tensor. So that in there is in general a 16-component object. So this tensor G is called the Einstein tensor. Basically, that is the gravitational content of the general theory of relativity. On the other hand, this tensor right here at the right-hand side, that's capital T subscript small ab, is the stress energy tensor of the matter field. So that's basically the matter content of the universe. So without matter, you could just imagine the right-hand side to be zero. So that's the Einstein equation, and perhaps one of the most famous quotes, which tell us about the content of this equation, is this one given by John Wheeler. This basic Einstein equation, or GR, basically tells us that space-time tells matter how to move, matter tells space-time how to curve. Yeah. So then, so in the general theory of relativity, it could actually account for several things that Newtonian gravity alone could not account. For example, the precession of the perihelion of Mercury. So that actually convinced Einstein that he came up with the correct gravitational theory encompassing Newton. But then again, I've mentioned as well earlier that in the general theory of relativity, gravity affects everything, so including light. So we have as a consequence of that the gravitational bending of light, which was detected early in the 1990s. And then also combining this with the idea that the observations of the many the light coming from the many galaxies around us, done by Hubble using database Sleeper and Vestas Sleeper in the 1920s, then he was able also to come up with the idea that the universe should be expanding, and that is also another consequence of the general theory of relativity. So Hubble's very famous observation is shown here in this plot right here as well. So that comes from Hubble's original paper. Yeah. So one important thing about the Einstein equation is that it is a nonlinear equation in the gravitational field, and that is a very important fact because it means that gravity would be able to source itself. So that means basically that even though this right-hand side is zero, then you'd get non-trivial gravitational space-time backgrounds, and the most exciting of which is a black hole. So it's a vacuum solution, there's nothing in it, but then you get basically a space-time in which the exterior is disconnected from, the interior is, the exterior is disconnected, causally disconnected from the interior of the space-time. So that's a black hole. And I'm sure you've heard about the more recent breakthroughs in gravitational wave astronomy. So in 2015, we finally measured, the LIGO and the Virgo collaborations finally measured directly gravitational waves from a binary black hole merger, and that is shown in this left plot right here. And then of course, I'm sure you've seen this picture. It took basically the scientific community, the social media by storm last year. An optical picture captured by the Event Horizon Telescope of the supermassive black hole residing at the core of the M87 galaxy. So you could imagine it right there, just sitting at the center of M87 galaxy, supermassive black hole that is billion times more massive than our sun. So yeah, So now I'm going to the much larger distances. So to explain cosmological observations and using GR as a framework, we'd have to combine the idea of GR and particle physics. So that would bring us to the roughly the standard model of cosmology today. And by doing so, the dynamics of the universe, at the very least at the background level, would be captured by these equations right here. So these are called the Friedmann equations in GR. So we have the left-hand side of the first equation is basically the gravitational content. Non-expanding space-time would have capital H is equal to 0. Capital H is known as the Hubble parameter. The right-hand side of the equation is basically the universe's fluid content, or you could call it the energy budget if you want, which is made up of the things that we are familiar with in particle physics. We have baryons, radiations, and neutrinos and other things. So then the surprise came in the 1990s when finally measurement of the distance modulus versus redshift of supernovae has been measured, and it turns out that the best fit to this data from a cosmological theory extrapolated from GR requires the existence of many dark fields, and in particular 2 dark fields. That is dark matter and dark energy. And from that, the lambda CDM theory emerges. So the equation for the lambda CDM theory is shown, the gravitational equation for the lambda CDM theory is shown right here. So in contrast with the Einstein equation that I have shown earlier, you're going to see here a modification in which the left-hand side is, there's a new term in the left-hand side, lambda GAB. So lambda in there is called the cosmological constant, which is what we associate as responsible for the observed late-time cosmic acceleration of the universe. So it turned out that the universe is not just expanding, this expansion is accelerating as well. Yeah, and more recent measurements would lead to the following energy budget of the universe today, shown here in this pie chart. So this comes from Planck data. You could access that from the NASA website. So we see that by extrapolating GR to cosmological scales, we require the existence of dark fields. The universe today is roughly 70% dark energy and 23% dark matter. So by dark, it means that these fluids could not be probed with electromagnetic observations. And well, most of our astrophysical and cosmological observations before gravitational wave astronomy come from electromagnetic observation. So cosmic acceleration could, of course, signify that it may not be that straightforward to extrapolate GR, which is extremely accurate at solar system scales. It's not straightforward to extrapolate that to cosmological scales. And because of this, we have some open problems related to lambda CDM cosmology. So here are some of the open problems. What sources the late time cosmic acceleration? So we call basically this the dark energy, but then fundamentally, what is this dark energy? So that's an important problem today. Another important problem is this: why is the measured cosmological constant lambda very small? So it turns out that the cosmological constant lambda measured by local and CMB observations, in fact, it's just the right amount of lambda enough to not rip apart the universe. On the other hand, theoretically predicted value for the cosmological constant from particle physics deviates, is bigger than this measured lambda by at least 50 orders of magnitude. So that is a very, very big problem indeed. So why do we have two different values of lambda? What is dark matter? If it's there, then we should be able to measure it using our, should we be able to measure it using our particle detectors? And then what are the initial conditions of the universe? So our picture from physics is that by evolving basically the dynamical equations of a theory, then we should be able to get to something which is the observable universe today. So then what are the initial conditions of the universe? What was there at the very, very beginning of the universe? Well, this is an important one. Is GR the final theory of gravity? Well, that is an important and controversial one. Yeah, so the questions highlighted in yellow would be we're going to touch on these questions in this talk. So it turns out that one of the possible ways to resolve these issues is by adding additional fields into the theory. And by additional fields, we have actually several choices from that. We could add a scalar field, one component, vector field, 4 components, and a tensor field. We could do that, 16 components. And by adding just a single scalar field in addition to the metric that is already sourcing the gravitational field in GR, this leads us to scalar tensor theories. And yeah, so that is the topic of my thesis. So yeah, we have a new theory right here, and to basically address the questions highlighted in yellow earlier, the first step in analyzing any new theory is to obtain the solutions of its field equations. Yeah, so the objectives of my thesis are then as follows. So basically, I would explore local and cosmological solutions in a scalar tensor theory, and then I would describe black hole perturbation. So we'll get to that in a while. So now let me just talk a bit about, in general, alternative theories of gravity. Yeah, so GR is known as the unique theory of a massless spin-2 field or tensor field. So several ways are known in the literature to make a theory that deviates from GR. You could add into the theory massive gravitons, and it would lead you to this upper branch. Like here, you're going to get the massive gravity theories. You have your DRGT described by basically for, as far as I can remember, for gravitational wave degrees of freedom, in contrast with GR, which has only 2. You could also to make a theory that is not exactly GR for cosmological scales, to break the assumptions of GR. And these assumptions are not, so you could, for example, assume non-locality. You could assume Lorentz invariance violation, leading you to, for example, a Java and Einstein ether theory, or you could add new extra dimensions into the theory. Yeah. But of course, the topic of my thesis is in this branch. As I said earlier, we're going to add an additional field into the theory. And by doing so, we have 3 choices. We could add a scalar field, a vector field and a tensor field. But the simplest of which is of course the scalar field, and then this would lead us to this lower right branch right here, that is scalar tensor theory. Yeah, and because adding a scalar field is also the simplest way to accommodate deviations in GR. You see that this scalar tensor theory branch um, has many branches compared to the vector and tensor branches. Yeah. So the topic of my thesis would go to this go further down this branch, would go to from scalar phi to Horn-Desky, and then it would go down to KGB. So I'd explain that. So in scalar tensor theory, another way to think of that is to simply, sorry about that. In contrast with the lambda CDM theory, in which you just added basically this term, lambda GAB, into the Einstein equation, we'd add stress energy tensor for the scalar field. So that is now a new part of the gravitational field. And in a scalar tensor theory, in contrast with GR, the gravitational field is now described by a metric field. So we have here GAB, but also by a scalar field phi. So now anyone asks what the scalar field is in a scalar tensor theory, it is the gravitational field. And we want basically the scalar field to activate at cosmological scale, so it would be able to address the problems with extrapolating GR to cosmological scale. Yeah. So well, just to make this a lot more formal, the action for any theories could be very well expressed in just one equation. So the action of a scalar tensor theory could be expressed in this way. So for theorists, we love this. So the GR part of this equation is the first term on the right-hand side. So without the second term, you could just imagine GR emerging from this theory. You vary this this functional with respect to the metric, which is the geometry of space-time in the scalar field. You could, if you want, call it the dark energy field. So vary that, then you get to the field equations of scalar tensor theory. Yeah, so the first term is the GR. What makes this a scalar tensor theory is now the second term. And the quite generally, to get to scalar tensor theory with second order field equations, this Lagrangian L would be a functional only of phi, the scalar field phi, and this kinetic term in the second argument of the functional L. So that makes it a scalar tensor theory. Yeah, so we see here that we actually have a lot of theory space to use to account for observations, but of course it is important to ground our theories to more phenomenological grounds. So we'll do that later. But first, let me just introduce Horn-Desky theory first. So this is the most general scalar tensor theory with second order field equations. It is described by four potentials G sub I. So this is a function of the scalar field phi, and in this capital X is just the kinetic density of the scalar field. You could think of this as a generalization of the kinetic energy for the scalar field. So the action of Horn-Desky theory is shown right here. So yeah, so we could partition this into four parts, each describe just a single G sub I, so that the L2 part is described by G sub 2, and the L5 is described by G sub 5, and so on. So we see there that for any choices G, we get a second order field equation. So this is a very powerful theory. So for this reason, it encompasses many of the well-known scalar tensor theories developed in the literature. For instance, quintessence is a Horn-Desky theory described by the following potential G sub 2 x minus v of phi, where v is an arbitrary function potential of the scalar field phi. Brandt's-Dicke theory is another really famous scalar tensor theory. It is a Horn-Desky theory with the following potentials G sub 2 and G sub 4. So we have here mass Planck squared. We have a constant omega. We have the kinetic density over phi minus v of phi. There's again an arbitrary potential v of phi. And then the G4 function is given by this, so it's linear in phi. So that leads us to branch leaky theory. And I should also mention that FR theory, so this another very well-known modification of GR, is in fact a scalar tensor theory when one identifies the scalar field to be given by this. So f of R theory is characterized by small f, the function of the Ricci scalar. So when you identify the scalar field as this mass Planck times capital F, where capital F is the derivative of small f with respect to R, then you'd get to our Horn-Deskey theory with the following potentials G2 and G4. Yeah, so we see indeed that there is large theory space that could be used to fit our observations, but yes, it is important to also impose observational constraints into this theory. So in this way, would actually make it much more powerful and more useful phenomenologically. So an important gravitational wave astronomy constraint that basically have narrowed down the viable space of in general alternative theories today is this GW17817. So this was the observation of gravitational waves from a binary neutron star merger, and in contrast with the merger of two black holes, so black holes would not emit electromagnetic waves. So this event GW17817, as it comes from the merger of two neutron stars, has an optical event following the gravitational wave event. So by basically measuring the time delay between the gravitational wave and the counterpart optical event, we'd get a constraint to the gravitational wave speed. And this constraint turns out to be this, that the gravitational wave propagation has to be very nearly equal to the speed of light. The error to this measurement is of the order 10 to the minus 15. So that is a very strong constraint. And the thing is, when you construct alternative theories of gravity, you are likely going to end up with theories in which the gravitational wave propagation is not equal to the speed of light. So yeah, this constraint would actually narrow down the search basically to those scalar tensor theories only in which the gravitational waves would travel at nearly the speed of light. So the most straightforward subset of Horn-Deskey theory in which the gravitational wave speed is equal to the speed of light is given by this action right here. So in contrast with the full Horn-Deskey theory with 4 potentials earlier, we now have just a gravity theory in which the gravitational field is described by 3 potentials. We have F, K, and G. And now, without further ado, going to the topic of my thesis, my main concern is for kinetic gravity braiding, for which capital F is selected to be this, just a constant. And then, well, calling B basically as the D'Alembert of phi. So the D'Alembert is box, it's basically the wave operator in curved space-time. So we get to this theory described by the scalar field Lagrangian right here. So this is known as kinetic gravity braiding. In the literature, some would call it a generalized cubic Galilean theory. So even with this being described by only two free potentials, K and G, it turns out that this is still very, very powerful. So some of the desirable features of KGB are the following. So it has self-tuning, which is basically a feature which allows us to screen a large cosmological constant into a small effective one. So it predicts the existence of hairy black holes. So I'll talk about that later. Yeah. And still being described by a scalar field, which would activate for cosmological scales, it would be very useful for dark energy phenomenology. And this is one of the most studied implications today. And I should also mention that it is possible for KGB to in fact be the endgame of scalar tensor theory should future cosmological observations still support GR. Yeah. So now on to my own results. So let's talk about compact objects. So so here's a picture of a compact object. Of course, we have here the billion solar mass supermassive black hole at the center of M87 galaxy. So that's very, very compact. So let me just deal with some definitions here. So by compact objects, we mean roughly gravitationally dense objects. And from GR, the most gravitationally dense objects that we know of are the following. We have neutron stars, black holes, we have wormholes, and these compact objects are described in their exterior by stationary geometry. So I'll get to that later as well. So the objective of my thesis in this part is the following: I would show you stealth black holes in shift symmetric kinetic gravity braiding. So stealth black holes are basically those which black holes of scalar tensor theory, which pretend to be the same black holes in GR, but they are actually not because there is a non-trivial scalar field in the background. And then a very important result is this. I would show you an algorithm. We call it hairdressing Horndeski. Basically for obtaining static and spherically symmetric solutions in KGB. So this is important, of course, because metric theories of gravity such as GR are described by nonlinear field equations, and it is in general very difficult to obtain exact solutions of this. So here I would provide an algorithm that would lead to exact solutions of scalar tensor theories, which could be later on used to compare with observations. Yeah, so let me just talk about a black hole a bit. So the most basic black hole that is there is one that should not be rotating, and a non-rotating black hole in GR is called a Schwarzschild black hole. So the anatomy of this black hole is shown right here in the left plot. So what characterizes a black hole is the event horizon of the space-time. So this is what partitions the interior from the exterior of the space-time. So that means that when you are inside the region partitioned by the event horizon, you won't be able to get a signal to your friends outside. So you're going to be stuck in the interior of the black hole. Yeah. So well, a very nice way to think of this actually is by looking at this whirlpool right here. So you have a whirlpool, and yeah, that is of course characterized by the speed of the fluid in that whirlpool. And so imagine yourself then attempting to row outside that whirlpool, but at just the right speed enough so that you could actually escape a certain region of this whirlpool, which you could actually call the event horizon. So if you're now inside this event horizon of this whirlpool, you will be, your future would be definitely eventually go to the singularity of that whirlpool. You're going to run into the center of the whirlpool. So you're just going to fall down there. Alternatively, if you're outside this whirlpool, still it's fine. You could get to anywhere. You could get far away from that whirlpool, get far away from the drain because you are outside of the event horizon. So let me describe what the hair means in scalar tensor theories. So by first, of course, describing what hair means in GR. So in GR, it turns out that black holes are described only by a mass spin and an electric charge parameters. So this idea is captured by the well-celebrated no-hair theorem of GR. So in that sense, we call the black holes of GR as bulbs in the broader context of scalar tensor theories. So in scalar tensor theories and alternative theories of gravity in general, black holes could actually be described by something else. So not just by a mass, spin, and charge parameter. And that is, of course, that could be expected because we're adding a new field into the theory. So this additional hair, as we call it, should be observable, for instance, through gravitational wave observations. So that's fine. That's very, very nice. Black holes in scalar tensor theories could be characterized then as follows. So bulb black holes are basically those which seem to be GR black holes. They would be described by a mass, spin, and an electric charge parameter, and by a trivial or a constant or zero scalar field. So the theory basically reduces to GR at the background level, a scalar field stress energy tensor. The energy of that just vanishes. You just get GR, you get a GR black hole. So those are bulb black holes in scalar tensor theories. On the other hand, now that we have new fields entering the theory, our black holes could be described by a mass, spin, and electric charge, but also by a non-trivial scalar field. And this is what we call a stealth black hole, because by just looking at the trajectories basically of objects falling into the black hole, we'd say that these black holes are those same GR black holes, but we don't see the dark field hovering around it. So it pretends to be a GR black hole, but it's not. Of course, because of the addition of new fields, we could expect new black holes in scalar tensor theories, and this could be described by other parameters, A, B, which may not be the mass of the black hole, the spin, and the electric charge, and still by a non-trivial scalar field. So that is what we could regard as a new Hairy black hole in scalar tensor theory. Now, on to my results. So I would like to present you this important result. Stealth black holes in shift symmetric kinetic gravity braiding. So my main result here has been obtained in collaboration with my advisor Ian and John Celestial, a master student of the gravity group. Yeah, so we found the following important results. So for stealth black holes to occur in shift symmetric kinetic gravity braiding, and that means that the space-time is described by the Kerr anti-de Sitter solution of GR. So just imagine the same rotating black holes that you see in interstellar. But in addition to that, it would be described by a non-trivial scalar field. So you have here the derivative, space-time derivative of phi should not be equal to 0. So that is a stealth black hole. So for black holes like this to exist in kinetic gravity braiding, the shift symmetric sector, they should have the following properties. First is the kinetic density of the scalar field should actually be a constant. And in addition to that, the potentials K and G describing the kinetic gravity braiding theory would have to satisfy this. So the first derivatives of the potentials K and G evaluated at the background should vanish. And with that, we obtain basically all of the stealth black holes in shift symmetric kinetic gravity braiding. So that is my first important result in this thesis. Now, I just want to show this new hairy black hole that I have also found using an algorithm that I would show earlier. So this is an example of a hairy black hole in kinetic gravity braiding, in which your space-time is described by this static metric here, where the metric functions h and f are given by these expressions right here. So the event horizon of this black hole is located at x is equal to 1. So yeah, so that's the base. I have basically described the geometry of that black hole. In addition to that, this black hole is characterized by a scalar field kinetic density shown right here. So this capital X that's non-zero, that describes the scalar, basically the non-trivial scalar hair of this black hole. Just to show you a plot of the metric functions of that black hole, you see a plot here of the metric functions FH. So you see here in this left plot that they would in fact, you could confirm this yourself. My codes are public in my website. So this metric functions H and F would in fact vanish at the same radial coordinate R. So there is a non-trivial Ricci scalar describing that we indeed are talking about the curved space-time background here, shown by this dotted green line right here. But of course, that's just a space-time geometry. What makes this a hairy black hole is the existence of this capital X right here. So we see here that X is not equal to 0 outside of the event horizon. We see that the black hole is indeed described by a scalar hair outside of the event horizon. For those interested, here is a plot of the geodesic potential of the black hole. So this is what could be used in the future to describe orbits around this new hairy black hole. With this, we should be able to impose solar system constraints into this theory. Other things could be done as well. Many other things could be done. Yeah. So so I have obtained this new hairy black hole by actually first developing this algorithm for obtaining static and spherical symmetric space-time. So this is an important work because it is in general very unlikely that exact solutions in scalar tensor theories would be found. But here is an algorithm for actually doing that. So for the KGB described by this action functional right here, yeah, so the K is basically X plus capital L. You have the braiding potential as a function of the kinetic density only. We assume a static and spherical symmetric ansatz, so that basically means that for any free functions appearing in our space-time geometry and the line element, including the scalar field, should not be functions of the time variable, the small t right here. So here's an algorithm for obtaining H, F, and phi. So that is that would be the geometry, including the background scalar field in a scalar tensor theory. So with tie that to a specific scalar tensor theory. So the algorithm is as follows. First, we will have to specify either F and H, and then use this equation, first equation in the box to determine the other one. Small q is the logarithmic derivative of H with respect to the radial coordinate. Then step 2 is given by this, determine the kinetic density of the scalar field in terms of the radial coordinate. So it's given by this expression. Now we're going to determine that as well in terms of the metric function. So it's given by this second equation in the box. Then the last step of this algorithm is, so we now actually have the F, H, and phi. So we have the geometry and the background scalar field. We have to tie that to a scalar tensor theory. And that is, we ask the question, what is this braiding potential capital G as a function of X? And to determine that, we'd have to use this third equation right here. So this would determine basically an exact solution of scalar tensor theory. And yes, that is an important result of my thesis. Yeah, so now let's jump to cosmological distances. So this, this is of course what motivates scalar tensor theories. So just for you to enjoy, here's a picture of the Hubble deep field, a picture of many galaxies captured by the Hubble Space Telescope. yeah, so hope you enjoy that. So now we're jumping to cosmological distances of about 100 megaparsecs. So that is, as far as I remember, about 10 to the 21 kilometers. So it turns out that for cosmological scales, the universe is spatially homogeneous and isotropic. And that means that we look anywhere, we're actually going to we're going to nearly see the same thing. And one evidence of that is by through the CMB, the cosmic microwave background. And observations of the CMB are the observation of the CMB is captured by this plot right here. So that's from the NASA website. So it turns out that you have a microwave signal detector. You point it to anywhere you want. You nearly get the same temperature of 2.7 and 2.7 Kelvin. So that's yeah, that's very cold. The spectrum around describing the intensity of the radiation is of the Planck spectrum. And most important to us, the fluctuations about this average temperature is very, very small. So you point your detector anywhere, you're nearly going to get it. So that is that is an important could be an important consequence of spatial homogeneity and isotropy. So universes like this, cosmologies like this in GR, in metric theories of gravity, should be described by the following spatially flat metric. So given by this line element right here. So for those of you familiar, for example, with the line element in special theory of relativity, this small a, which we call the scale factor of the universe, would just be equal to 1. Now for an expanding space-time, we'd include this small a right here, and then the Einstein equation or the field equations of scalar tensor theory would in general predict how A would evolve in time. So increasing values of A in time would mean an expanding universe. Decreasing would mean a contracting. Expansion could be accelerating. So this predictions should be captured by the field equations of the theory. So the objectives of my objectives for this part of the thesis is to obtain background, again, exact background cosmologies in scalar tensor theory in KGB. And then I would present you a cosmology designing algorithm, again, a very important one for assigning a specific evolution of the scale factor to a specific scalar tensor theory. And that is again important because it is highly non-trivial task to obtain exact solutions of scalar tensor theory. Yeah, so that is my second objective. So just to get us all at the same page, so here's what we mean by an expanding universe in metric theories of gravity in GR scalar tensor theory. So you could look at this left picture right here. For example, you see that there are points, for example, describing the locations of different galaxies. We're at the center of the balloon. As time would pass, the balloon would expand. So we see that the distance of the points would actually increase, measured on the surface of the sphere. But still, with respect to the center, we'd actually measure them with the same angular coordinates. And yeah, because gravity affects everything, almost everything. Everything, yeah. So it would affect all physical lengths. And a very important consequence of that is the stretching of wavelengths when they travel to cosmological scales. So you could imagine, for instance, this picture right here. You have an emitter of a signal located A, and then a receiver of the signal B. And the signal was then emitted at an earlier time. Then by the time the signal has reached the observer at B, the space has expanded by already a significant amount. This would stretch the wavelength of the emitted radiation, and this is what we call as the cosmological redshift. Yeah, and just to show you here what could actually happen in in an expanding space-time, again, the dynamics is captured by the so-called scale factor. For example, looking at this curve one here, this basically describes a universe that would expand, but then eventually it would reach a certain point where it would start to contract. Then you could have this other curves here, 2 and 3, in which the universe would just expand and expand in time. So the dynamics of the universe is captured by the Friedman equations in GR. In a scalar tensor theory, the Friedman equations would instead look like the following. These are the Friedman equations highlighted in blue. We have 3h squared is basically 8 pi rho. Rho is the energy density. Capital P is the pressure. So the time derivative of h, which is the Hubble parameter, the logarithmic derivative of the scalar factor in the time variable small t. The dynamics of that is sourced by the pressure in here. Well, we have on the other hand, of course, the matter in the space-time would move on geodesics, and following the first law of thermodynamics. So we have this third equation right here, basically describing how the matter would evolve as the space-time would expand or contract. Just to get you to understand what again what an expanding or what a dynamical universe is, for a non-dynamical universe, capital H would just be equal to 0 for any time. So what makes this scalar tensor theory is this dark energy field right here. So this is capital Pi. So in this way, this energy density would be described by matter energy density and dark energy density, same as the pressure would be partitioned with that. The energy densities and the pressure of the scalar field are then given by these last two equations right here. So this is valid for kinetic gravity braiding. So these are the equations that describe the dynamics of the universe in a kinetic gravity braiding. Just to show you what several outputs of the algorithm that I'm about to show later, here's a concrete dark energy theory. So the action functional for this theory is shown right here. In terms of KGB, this is described by the following potentials highlighted in blue. And it turns out that this theory is very interesting because it accepts an accelerating universe. So this is a desirable feature because of the observation of late time cosmic acceleration. So this could describe an accelerating universe. In addition to that, this theory is in fact self-tuning as well. So it means that it has the feature of screening a bare cosmological constant lambda in a small effective one. So as you see here, the inflationary solution is described by this capital H naught right here, but this capital H naught is sourced by this by the constant appearing in the braiding potential of the theory. So it's not sourced in any way by the bare cosmological constant lambda. So that makes it self-tuning. This is also interesting for the reason that hairy black holes could in fact be found in this theory, and was from a paper published in December 2019, as far as I remember. Yeah, so other than that, here are theories which basically tries to pretend to be GR theories, but with a non-trivial scalar field. So in GR, a matter-dominated universe is described by a scale factor with which is expanding as t raised to the 2/3. In a kinetic gravity braiding, a solution like this could in fact be accommodated by this braiding potentials right here. K is x minus 2 lambda. Capital G is given by this expression right here. So there's a logarithm. Also, Um, in GR, radiation-dominated universe, the one which is in which the energy density is based primarily just dominated by radiation particles, very fast-moving particles, neutrinos, photons. The scale factor of the universe would depend on the time as t to the 1/2. It could be accommodated in a scalar tensor theory with the following KGB potential. So K is again x minus 2 lambda, and here's the braiding potential for a scalar tensor theory, which looks like radiation dominated universe in GR. So now let me describe an algorithm for obtaining in general any expanding space-time in scalar tensor theory. So we focus on this action functional right here. So again, we have the Ricci scalar describing the GR sector of the theory. We have this k is x minus 2 lambda, and then we have an arbitrary function g at this point. And then we impose spatial homogeneity and isotropy. And then we also want the scalar field to depend only on the time variable. Yeah, so the algorithm for obtaining any expanding space-time solution, fitting them to a specific KGB theory, is given by the following. So first, we want a cosmological space-time, which is of course the observable in here. So we're going to specify that and then solve. The first step is to solve for the matter energy density of the space-time by solving this equation right here. So the first equation in the box would determine the matter density corresponding to the background space-time. And then the kinetic density of the scalar field, which is of course the dark energy field here, should be determined using step 2. So it's given by x is given by this equation right here, phi dot squared over 2. Could be also determined by specifying the rho and a that we have determined from part 1 of the step 1 of this algorithm. So this determines the kinetic density as a function of time. And then lastly, of course, we want to tie the solution to a scalar tensor theory. We're going to have to invert this x as a function of t, and then we'd use this last equation right here to determine what the braiding potential should be. So at the end of this, we're going to obtain an exact cosmological space-time solution of scalar tensor theory described by a scale factor and the matter density rho, and then a scalar field phi in a kinetic gravity braiding with this potential g. So that would be the important output here. And yeah, so just to show you how general this algorithm is, here's the scale factor basically predicted in lambda CDM theory. So in the lambda CDM theory, the history of the universe could be divided into several eras. There's a radiation era, there's a matter domination era. Today we call it dark energy era. So the classification depends on which fluid component of the universe dominates in energy. So this is the scale factor of the lambda CDM theory right here. So I could tie that to kinetic gravity braiding model as well. And by doing so, for instance, I would obtain a theory in which the dark energy equation of state is given by this right plot right here. Yeah, so for example, if I just fill the space-time with radiation, so that's given by an equation of state W, which is 1/3. So the dark energy equation of state would be given by this red line right here. By the way, the horizontal axis of the plot is the redshift. So today we live at redshift 0. So that corresponds to 1 in the horizontal axis. So yeah. So on the other hand, when I just fill the universe with non-radiative objects, matter, dark matter, I get to this blue dark energy equation of state provided by this blue curve right here. Also, I could fill the space-time, of course, with the same cosmological constant in lambda CDM theory, and then I would by doing so, I would in fact end up with this dark energy equation of state, which would be very nearly equal to -1 today. So that's one application of the algorithm shown earlier. Yeah. So now on to the last part of my thesis. I want to talk about gravitational perturbation. So now that I have actually,
Reina here. Can I
yes,
ask here?
yes, I think.
So because when we say that it's all either W equals 1, third W equals 0, or W equals -1, how about if in reality, or in the lambda CDM universe is actually a combination, the pie chart. Right? So how does that tie to your picture here?
Yeah. Thanks. Yeah. So far, I have actually the algorithm that I have shown earlier assumes first that the universe is filled only with one type of fluid component. So that fluid component is given by this equation of state W shown in the first equation in the box. But I just did that for just to simplify the equations for a bit. But it's actually possible to proceed by generalizing this equation, and we know how this would actually generalize. That's the first law of thermodynamics. In which case, instead of 1 plus W appearing in here, I'm going to transpose the rho in the denominator of the left-hand side to the right-hand side. Then instead of 1 plus W, we're going to have rho plus P. So in that case, we'd be able to accommodate an obviously more realistic scenario in which the universe would be filled with a mixture of different fluid components. Yeah, thanks.
Okay. And that will also be time evolving.
Yes, that should also be time evolving.
Right. But then we'll fit to your A of T.
Yeah, so because the different fluid, we're assuming that the different fluid components are non-interacting with themselves. So in that case, they would all just move in the background geodesics of their space-time. So for example, if you have an equation of state 1/3, your energy density would drop as 1/4 the inverse fourth power of the scale factor. If you're very slow, then your energy density would drop as inverse third power of the scale factor. Yeah, so they would actually evolve independently still.
Great. Thanks for the clarification. We'll have a follow-up after your presentation.
Yeah, thanks.
Okay,
thanks,
so
thanks for the
may I request to have Reggie finish first because the time is almost up. Except for let us allow Reggie to finish.
For sure.
Yeah. Thank you. So I'll wrap up in 5 minutes. So let me talk about the last part of my thesis to gravitational perturbation. Yeah, so we have exact solutions of scalar tensor theories, but of course it also happens that exact solutions in many cases won't actually describe what is realistically out there. This is what brings us to perturbation theory, and in the context of scalar tensor theories, this brings us to the topic of gravitational perturbation. Just to show you what it means, here's very nice picture right here. So that is from an artistic interpretation of a star, observing a star dancing around the Sagittarius A star, the supermassive black hole at the center of Milky Way. Yeah, you might have heard of that as well. Yeah, so let's talk about gravitational perturbations. So this is important for the following reasons. And by speaking about gravitational perturbations, I should say that I'm talking about mainly black hole perturbations. So it's important in gravitational wave astronomy because the way we build templates today is by combining basically results from post-Newtonian theory, numerical relativity, and black hole perturbation theory. So the late time stages of gravitational wave signatures from black holes neutron stars would turn out, in fact, to be dominated by their quasi-normal ring-down perturbations. So perturbations are important as tests of the no-hair conjecture. So basically checking if there is a hair out there, because if there is a hair, then the gravitational wave signature should be contaminated by the hair. It is an important also for analyzing the ring down, as I've mentioned already. The late time stages of gravitational wave events are dominated by ring down signals, perturbations of the background space time. Um, for the same reason that is important in gravitational wave astronomy, and I should also mention that in a few years would definitely witness the launch of LISA, a space-based gravitational wave observatory in which targets extreme mass ratio binaries. And for instance, that would we should be able to describe in their perturbations in which the order of perturbation is of the order of at least 10 to the minus 3. Yeah, and gravitational perturbations, as we are going to talk about black hole perturbations, should be important in strong field phenomenology, basically things around black holes. And yeah, out there, of course, we should also deal with cosmological observations, and there are a lot of work on this. Yeah, so just to imagine what a black hole perturbation is, in this lower left equation right here, this is formally what I do with the equations. I would write down the metric GAB as an expansion in the background space-time with a bar plus a small h, in which the components of small h are all way smaller compared to the G bar, and same thing with the scalar field. And so we could imagine what a perturbation here. You have here a nice picture of a sneezing ant now perturbing the background space-time of the black hole. Yeah, so that is a perturbation, and of course you could also imagine this small blob entering the black hole right here in the upper right picture. So the blob enter the black hole, disturbing the background space-time as it evolves, but then eventually the black hole would shed what it is it entered going back again to its stable thermodynamic configuration. Same thing, of course, could be observed in a pond when you drop a pebble in it. So waves would propagate in the pond, carrying information to the boundaries of the pond, and then it would settle down to a final equilibrium state. So my objectives in this part of the talk are as follows. So I would describe perturbations on bulb black holes in KGB, and then describe perturbations on hairy black holes in shift symmetric kinetic gravity braiding. So here are my results. So for bulb black holes, it would turn out that the scalar and tensor modes will be basically the equations for small h, the perturbation in the metric, and psi, the perturbation of the scalar field, would be decoupled. So provided that we have a bulb black hole then doing the perturbation, it would turn out that would end up with an equation for h described by the first equation in the box. And you see that this equation in the box does not have any, the first equation in the box does not have any psi in here. So h is decoupled from psi, and we could then proceed with this in the same way that we could proceed in GR. The equation for the small psi would turn out to be given by the second equation right here. You would of course recognize this to be just the massive Klein-Gordon equation for the field psi, in which the mass is provided by the displacements of the potentials right here. So yeah, that is important result because the perturbations are decoupled, and we generally won't actually expect that for scalar tensor theory. So to proceed with perturbations in Hairy stealth black holes, we could my approach would be to first investigate the perturbations on Hairy stealth black holes, which is my result in chapter 3 of my thesis. Again, for Hairy stealth black holes in KGB to exist, the potentials would have to satisfy these equations right here. But then to proceed, it would be also useful to decompose the perturbations in spherical harmonics. And by saying this, I mean that because we're dealing with, in general, an object which has many components right here, we have small HAB, and in general that should have 10 components. That is a symmetric tensor. So we're going to, instead of dealing with all that at the same time, we're going to separate the different components in spherical harmonics. Scalar, vector, and tensor spherical harmonics written down in the following way. So of course we are all familiar with the scalar spherical harmonics, and to build a vector from that, we just differentiate that with respect to the coordinates of the two spheres. To build a tensor of that, we could multiply the scalar harmonics with the metric of the two sphere. We could differentiate that twice with respect to the two sphere, and so on. And it would even turn out that because for the static, for spherically symmetric backgrounds, we would not have to deal with all of them at once. It would turn out that it is possible to talk about them separate in parity. And by parity, so for example, odd parity would mean that when you rotate your vector in the other way, so imagine just you have an arrow and that you point it to the other direction, you're going to get a factor in your transformation that is -1 raised to L plus 1, where L is the spherical harmonics coordinate. For a vector, you're just going to get, for an even parity harmonics, you're just going to get -1 raised to L. Yeah, so it would turn out that the odd parity components would actually not be modified by the scalar hair. So let me just jump to the final result of my thesis. So the even parity perturbations of the on gravitational perturbations on L-Hairy black holes are described by this master equation right here. So the master equation is this equation in the box. So that should be a bit familiar. That looks like the Schrodinger equation in quantum mechanics. So this one is called as the Rayleigh equation in GR. However, in contrast with just the Rayleigh equation in GR, the contribution of the scalar field in this equation comes in the form of this effective scalar field source term in the box right here. So if we're just talking about GR, then what you need to do to obtain the master equation is to just remove the effective scalar field source term, and that would lead you to the Rayleigh equation. So in the important result here is the existence of this effective scalar field source term, which is in all ways we could regard this as the scalar hair of the perturbation. And then finally, so what I actually just talked about are valid for harmonic index small l greater than or equal to 2. For small l is equal to 0, for example, we know that the harmonic spherical harmonics y is just constant. So in this case, the derivatives would all just vanish. So that requires separate treatment. And the case with small l is equal to 1 would actually also require separate treatment. Yeah, so let me just finish this. So for the monopole perturbation, L is equal to 0, the even parity sector would be described by this equation in the box. So that so in GR, the counterpart for this would actually be a gauge mode. So it's a gauge mode corresponding to just the mass shift of the black hole space-time. So that is an important result, because this equation in the box, that is a correction to the background space-time, is not a gauge mode, and it could not be removed by trying any gauge or coordinate transformation in the theory. So it's there. So it could be observed. It should be possible to observe this if it's there. So for the dipole perturbation, L is equal to 1. Again, the odd parity perturbations are unmodified. So the odd parity perturbations would be the same as in GR, turning the black hole into a turning the static black hole into a slowly rotating one. The even parity dipole modes would, on the other hand, be modified by this expression right here. So in the blue box right here. So this in GR would be a gauge mode. It would correspond to a center of mass shift, but in other than that, I'm getting this new term in which again we see here Q of omega, which is the residue of the scalar field or perturbation appearing in the master equation. So that is an exact solution to the even parity dipole perturbation. And well, yeah, so let me just end this in 2 minutes. So let me summarize. So in my thesis, I have explored background and perturbative solutions in scalar tensor theories. Specifically, I have dealt with black hole and cosmological solutions. I've shown you a bunch in this presentation. Many other results are available in my thesis. For the reason that I have also obtained background designing algorithm for which basically ties a provided geometry to a scalar tensor theory. And the importance of that, again, lies on the fact that it is, in general, very difficult to obtain exact solutions. And exact solutions are, of course, important because this is where we start analyzing what the content or new contents of a scalar tensor theory is as compared to GR. Gravitational perturbations, I've dealt with that. I've shown you very interesting results. So the even parity perturbations would be modified. I've shown you what the scalar hair residue would be at the level of the perturbations, and I've shown you exact solutions for the monopole and dipole perturbations as well. So those are the results of my PhD thesis. So possible future work are the following: screening mechanisms. So for very weak fields, we want the scalar tensor theory to describe what GR describes in the solar system because it's very accurate right there. So that's one desirable feature. And there's actually a recent paper on this, a very recent one, and a good paper on this. Also, it is possible to do cosmological perturbations, but there are actually a lot of work on this already, ongoing work and projects. But still, there is room for work in there. Possible future work is to analyze, narrow down scalar tensor theories with self-tuning mechanisms, basically those which could automatically help us avoid the cosmological constant problem. Why is the observed cosmological constant so small compared to the predicted one by vacuum fluctuations in particle physics? And then finally, more work is needed for gravitational perturbations, specifically in black holes. So there are actually not a lot of work dealing with perturbations specifically in hairy black hole backgrounds in scalar tensor theory. Understandably, because in general, you're not going to end up with just a single master equation. And in general, the equations are actually very, very long. They're difficult to interpret, among other things. And yeah, so that is my talk. Here are my the paper cited in this presentation. Here are the figures. I've taken the figures from these links. So that's it. I'd like to thank Gravity. It was a nice 3 years. I'd like to thank NAP and UP. It was spectacular 10 years. It was great. Thank you. So that's it.
Okay, thank you, Reggie.
Thank you, Ma'am V.
Let us start with the panel members first. If they would like to ask questions from the audience, please send a chat so that I can order you in line after the panel members. Can we start with Dr. Reyes?
Yes, thank you. So, yeah, my question is actually just a follow-up of my earlier thread, which is on the cosmology. So just want to understand the interplay between the KGB theory parameters and the actual composition of the universe, the matter, radiation, and dark energy in reproducing the A of T in your model.
Yeah. Thanks. So in general, the most general way to proceed. Yeah. So let me just talk about the this Taylor and cosmologist again. So well, what I'm doing here is to basically tie specific cosmological observation, assuming that we could of course measure this small A of T, so that is the scale factor of the universe, and then tie that to a specific kinetic gravity braiding model. And the first step to do that is to determine what should be the matter energy density that would be compatible with this scale factor. So this first equation right here is in fact, I should mention that while this looks like just the first law of thermodynamics in GR, that in fact turns out to be a necessary condition for the field equations in scalar tensor theory. So that has actually surprised me at first. So the more general version of that, in fact, would be this equation right here. So this first law of thermodynamics equation, this third equation right here. So to proceed with cosmology, in which we have a mixture of different fluid components, of course we want there to be radiation and matter components, dark matter and baryonic components, among others. We're going to have to proceed by basically supplying what their pressure and energy densities are in this equation first. So actually just the pressure first, and because they're non-interacting, these fluids are non-interacting, we could it would be possible to generalize this equation to this, and then with that, after doing the first step right here, we should be able to obtain a constraint to the actually a constraint to the energy densities of the matter and radiation components. Yeah, so that would be a generalization of this algorithm shown right here, which would actually be very nice. So of course, the simplest version of that is just provide one fluid component.
Right. So in this case, it's just
yeah. So yeah,
component that you want to put in, and then the K, the G will adjust accordingly.
Yeah. Thanks.
Right.
So just for simplicity, I have assumed in this equation that P is equal to W times rho, and then well, with that we're going to get the energy density that is compatible with the scalar field A, and as expected from the first law of thermodynamics, and then from that we determine what X is, and then determine what the theory should be, provided this this small a and small rho.
That's clear. Thank you.
Yeah, thank you for the question.
Dr. Esquera.
Okay, a quick follow-up to Dr. Reyes' question. Okay, if you start with the more realistic scale factor, the inversion involved in step 2 might be more difficult, right?
Yes, yes. Yeah, thanks for the question.
Yeah, but
So the important assumption in here, and this is what actually would differentiate between the make this algorithm work, is that this capital X should have an explicit time dependence in the right hand side of this equation. So for example, this algorithm won't work if it would turn out that the right hand side provided by the second equation in the box would actually turn out to be a constant. So in that case, of course, it would not make sense to invert x of t is equal to constant. Yeah, because that's what's that? That is a horizontal. That is a vertical line. Yeah, thanks, sir. I'm not sure if I have answered your question.
okay.
So, may I rephrase? I'll just step in as advisor. Maybe Dr. Esgara is also asking, can you perform this algorithm for the observed A of t of the universe?
Yeah. Actually, so for any capital A, well, for nearly any capital A, in fact, and this is actually in the thesis and in the paper, for nearly any capital small a, sorry, scale factor, this step 2 would lead to a kinetic density with a non-trivial time dependence. In that case, it would be possible to always determine a theory that is compatible for that given A, provided of course that we would end up with an observation of the scale factor, and then determine from that the matter contents of the fluid contents of the universe.
So sometimes it's not just so even if it's not explicitly invertible, I mean, you can always do it numerically, right? So
yeah. So that is in fact what happened in this equation, in this example right here. So I've used in this example the scale factor from lambda CDM theory. So the right plot derives from basically starting with the fluid components, the energy budget determined by lambda CDM, so that's 70% dark energy, 30% matter, and then using the Friedman equations to determine what the scale factor is. And then this would be the emerging scale factor from lambda CDM. So I've done the algorithm numerically, plugging this into the algorithm right here, and then for that I have obtained, and I'm shown in the thesis what the energy densities of the matter is, what the energy density of the dark energy field is, and well, I've just shown here what the dark energy equation of state of the scalar field phi is, provided that the scale factor is given by this equation right here, this plot right here. So in fact, for any except for just one equation, one scale factor, an oscillatory scale factor, also shown in the thesis, any other choice of small a could actually be used to obtain a unique KGB theory compatible with that scale factor A. Yeah, so I hope I clarified the I have been able to clarify this. Thank you.
Dr. Esguerra?
Okay, this concerns this concerns the first part of your results. It's not in the slides, but it's in your manuscript. Okay, in your
yes, sir, of course.
manuscript, or Okay, in your manuscript, there's this specific choice of the Ricci scalar where somewhere along the way you had an expression involving our favorite elementary function, right? The Lambert W function.
Yeah.
Yes. Now the Lambert W function has two
Thanks, sir.
branches. You did not specify which branch.
Yes, sir. So for that part of the thesis, I'm referring to just the principal branch of the Lambert W function in the thesis. Yeah. So thanks for the question. So
So the W0.
Yeah, the W0. Yeah.
Yeah.
So the same that
Why are
we
you
use in
avoiding
the
W in -1? Because you can still get a positive. You can still get a real R for W -1.
Yeah, thanks. Yeah, I'm not actually avoiding it, but I may actually have just not well, I may actually have tried it, but it didn't work. But I would have to check again. So I definitely would have tried many things way back. I mean, I have obtained this result in 2018. I think I may have tried it, but I'll check and
yeah, I think just
get back to you in this
maybe
question.
you'll get some new
thanks.
physics.
Yeah, thanks, sir. Thanks.
Further questions, Dr. Esguerra, or can we go now to Dr. Galapon?
Yeah, maybe one last question. So in much of this work, you frequently have to invert a transcendental function.
Yes, sir.
Okay,
yes,
and I think there's a 2002 paper where it was shown that one can get at least one root of the transcendental of this transcendental equation. Well, at the very least, one can represent this as a contour integral. And I wonder if, so suppose you have a contour integral representation of the inverse function, what further progress can you make?
Sorry, sir.
Okay, suppose it's possible to invert, to do all those inversions formally, okay? Let's say you can express all those inversions in terms of a contour integral. Okay. I mean, what further progress can you make if, assuming that's feasible?
Yeah, thanks. So, so your point is that this whole algorithm and the same one for actually the cosmology is requires the inversion of a transcendental function. In general, the equation involved is even in many cases nonlinear. So we get to actually the consequence of that is in general having to obtain different branches of solutions. So for example, in the slide shown here, in general, actually, if you try to specify f so sorry, you specify q instead of f, then you're not going to get to a unique unique theory g. You could get to somewhere that would not be the same, for example, if you specify the other metric function. So the first, if you observe the starting point of the algorithm is the first equation right here. So it doesn't treat q and sorry, it doesn't treat h and f at the same level. This is the first order differential equation in f, and it's linear in f. So providing f would actually lead to a unique theory. On the other hand, if you provide h, which is the other metric function in the line element, you'd get to more interesting, possibly wider subset of the theory if you provide H, because if you provide H, then this equation transforms into a nonlinear second order differential equation in the variable H. So for the inversion of this, so this transcendental equation, so the next equation right here, it is very likely that we'd get to many branches of the theory, theory potential capital G. So that is the consequence of that. And suppose that we, as you have provided, suppose that we could provide the inversion using a contour integral, then I think so long as we could, well, if I'm doing it, I could close the contour integral, then I should be able to make some progress. The next step of which is, of course, to most likely the next step of which is to determine the perturbations, make sure that the perturbations are actually making the background solution a healthy theory. Yeah, so have I answered the question?
So can you still solve for G of X? Can you get the theory parameter even if your inversion of number 2 leads to a contour integral?
Yeah, I think so. I think I can do that. So as long as for example, this example right here is purely numerical. So you could imagine that I've dealt with the counterpart equation for 2 right there. So both the first and second equations are completely numerical right here. And then I have inverted the equation 2 numerically. You see that it's quadratic, for instance, in the Hubble parameter. You have, though it is linear in rho, I've done the inversion numerically. So suppose that the inversion could be expressed as T contour integral in X. As long as I could get some very nice numbers, I think I can't think why obtaining the theory potential G would not be possible. So I think it should be possible as long as we could do numerical inversion of equation 2. Yeah.
Yes, that's my last question.
Thanks, sir.
So who's next? Is Dr. Villagonzalo still here?
Yeah.
Dr. Villagonzalo, did she get logged out or something?
Yeah, maybe she lost her connection. Did she? Hey, is Dr. Galapon around?
Okay.
Yeah, I'm here. I'm just waiting to be called up.
Okay, maybe I can read the questions from the. Oh, okay. Okay, so Dr. Galapon.
Okay, so is it my turn now?
Yeah, please go ahead.
Yeah, okay, sige. So
yes, you can ask.
Okay, sige. So Reggie, let's go to slide number 15.
Sorry, sir.
Slide number 15. 15.
15?
Yeah, 15.
15.
Yeah,
15?
Yeah.
15. 15. That's 15. So
yes, sir. Yeah.
Okay, so there I see your kinetic gravity braiding, your FP, and you said you made a choice for your FP, which is given by MPL squared over 2. So
yes, sir.
If I heard it right, so that was a choice you made for your F of phi. Why that choice?
Yes, sir. Thanks. So again, well, it starts with um, well, first, if we want the theory to be compatible with gravitational wave astronomy constraints, that the tensor mode propagation is very nearly on the light cone, then the easiest way to avoid that constraint or to pass that constraint is to assume a theory in which the propagation is the gravitational wave propagation, or the tensor modes would propagate at the speed of light. So the Horn-Deskey theory emerging from that is given by this action right here. So for any choice of F, K, and G in this equation, we would actually end up with a scalar tensor theory with tensor modes propagating on the speed of light. So it's so why the choice of F? It's actually just simple to try. Well, it's simple to in general, you could have an F in the theory action functional. But in general, it's simple to have to just set F to a constant. In this case, in this case, this coupling, in fact, between the scalar field and the Ricci scalar in the action would not be around, and we'd get to much simpler equations. But say, so I just actually have done that for simplicity. And well, at the same time, kinetic gravity braiding was other than that, of course, kinetic gravity braiding was obtained way before GW 1717. It was obtained in 2009 by generalizing the cubic Galilean theory. So it leads to that. So the thing is, if we do not set F to be equal to a constant, we'd have this what could be called a conformal coupling between the Ricci scalar and the metric. And that would be very important if we're dealing with theories in which, for example, we want to describe, for example, the interior of stars, which in that case, the scalar field could actually couple to the star's mass. So in general, if we're just actually dealing with vacuum solutions, it would, even if F is in here a function of an arbitrary function of phi, it would actually be possible to transform the theory into kinetic gravity braiding to this KGB action, Lagrangian, by a conformal transformation. But what would differentiate it is that if there's a coupling with a matter field. In general, of course, there is. So the most general case, and well, again, a possible future work would be to include an arbitrary function f of the scalar field in this equation. Yeah, I've actually done some work with this more general theory as well. So for example, in the result on bulb black holes shown in part 5 of my thesis, I've told you that the tensor and scalar modes would generally decouple for bulb black holes. This would not actually valid if I provide an arbitrary function f of the scalar field in this action functional. So the fact that the tensor and scalar modes in my chapter 5 actually decouples is dependent on the fact that I've set this function f, this conformal coupling function f in the action to this mass Planck squared over 2. Yes, sir. Have I answered the question?
I just wonder what is the underlying physical motivation of equating that to Max Planck squared, for example. Why why Planck mass? Why not some other mass?
Oh yeah, yes sir, yes sir. Thanks.
So why choose Planck mass? not some other mass.
Yes,
I
sir.
could have chosen the electron mass, or let's say, yeah, the electron mass. Why not electron mass? Or why Planck mass?
Yes, sir. It actually just stems from the units that we are using. Well, we typically use when dealing with gravitational theories. So in general, the constants appearing in the gravity theories are provided by the constants appearing in the Einstein equation. So that's the Newton's gravitational constant and then the speed of light. So for if we then say for example, Paul, we do not set well we set h bar equals to 1. Um, then in that case it would turn out, well, it actually turns out that this written down in the not in terms of Planck mass, would this coefficient in front of r would in fact be 1 over 16 pi c to the 4 over 16 pi g. So the constant in front of the Ricci scalar, not using any special units, is c to the 4 over 18 pi g. And then typically it just turns out that when we set h bar to 1, then it turns out that that constant in front of the Ricci scalar appearing in the Einstein-Hilbert action turns out to be the proportional to the square of the Planck mass. But I'm not really dealing with quantum mechanics here, so I do not actually have to call it Planck mass. I could have just retained this to be c to the 4 over 18 pi g throughout, but I felt that writing this down m Planck squared over 2 would be simpler for my equation.
So is that MPL? That's MPL squared. So I suppose that's supposed to be small. Is that small? In your units, is that small?
Yes.
How small is
Yes,
that?
sir. So that's c to the 4 over 18 pi. Well, that's not actually small. Yeah. So that's c to the 4 over 18 pi g. So that's order 8 to the 4. So 32 divided by, I mean in MKS units, capital G is order of 10 to the minus 9. So if I'm doing the arithmetic correctly, then it should be of the order 40.
Okay. So does that not make the first term negligible compared to the second term?
Not necessarily so, sir. Because in general, so of course the most general because what I'm showing here, sir, is the action functional of the theory, and it would actually be possible, for example, to say I provide a constant in front of the scalar field Lagrangian in the second term right here. I could, for instance, because this is a function an action functional, pull out the m Planck squared over 2 in here, and then in which case I would see a coupling between the two constants, basically determining the metric part of the theory with the scalar field part of the theory. So it could make it negligible compared to the second part, but then not necessarily so. So to do that, it would be important to first determine the field equations of the theory. Then it would be possible. Then at that stage, it would be possible to determine which constants, which are actually the independent constants of the theory.
Okay.
Okay, so I'm sorry I got disconnected. Are you done, Dr. Galapon?
Okay, so in the next round, I'll ask again.
Okay, can I ask, in your thesis figure 4.2, this is the scalar field kinetic density. Why is the case W minus 1, why is it has a different behavior? It does not scale in the same way with the energy density with the rest, like W0, W1/3.
Yes, sorry, ma'am. Because could you repeat the question?
Figure 4.2. So there is the kinetic density figure and the energy density figure. In the energy density figure,
Yes,
they
so,
scale,
yeah,
they scale W-1, W0, W1/3. But in the kinetic density, this is not reflected. The W-1 has a different behavior. Why is that?
I'm sorry, what page is this?
Page 89.
Yes, I'm just
4.2.
I'm just opening the thesis. Yeah. So figure 4.2. So that's
I mean, I'm just assuming that kinetic density should be reflected with the energy density. For the rest, they're okay. But for the case W-1, it does not. So what happened there?
Oh, yes. Thank you very much. Thank you for the question. Yeah. So we in figure 4.2 of my thesis. So I've not I've not shown it in my presentation. So I'm going to show it right now. Yeah. Yeah. So here it is. So this is figure 4.2 of my thesis. So this is the same example that I have described in the last part of the cosmology part of my thesis. So provided the lambda CDM scale factor, then the kinetic density is actually of the provided that we fill the universe with just radiation, matter, and cosmological constant fluids, then we'd get to this plot right here of the kinetic density of the scalar field. So that's the kinetic density. So for example, we're seeing that it generally decreases if we provide the space-time with radiation and baryonic fluids. It would, on the other hand, turn out to be a constant for late times if we supply the space-time with a cosmological constant. I'm not sure for if I'd answer your question correctly, but it's this kinetic density for the scalar field, if maybe this is what you're referring to, is almost just almost constant. So yeah, it's reflected right here.
But why is it not zero?
Yes, thanks. So why is it not?
So Reggie, so there are two plots you're plotting. There are two quantities you're plotting there: the kinetic density x, and then there's rho, right, which is your energy density.
Yeah,
right?
thanks.
Are they? What is their relationship?
I think gets ko na yung so why is it not zero? See, I have obtained that solution using this algorithm right here, and you see that the step 2 of this algorithm basically determines the kinetic density after providing the scale factor A and the Hubble parameter of the theory, and then determining the matter density. So this second equation in the box, you see that yes, there is a first term in which there's an energy content, rho, determining the energy content of the space-time. We have the h squared is an energy density, again, basically the energy density of the expansion. On the other hand, we see here that the cosmological constant enters this equation as well. So
Reggie, time out muna. Naglalag yung PDF. Hindi pa siya naka-display. Okay, kita na namin.
Okay.
Yeah, ngayon pa lang namin nakita.
Yeah. So thanks. Yeah, so you see in the third, yeah. So I'm not sure if I failed to mention this in the thesis, but I needed the kinetic density to actually be positive. So look at this equation besides the number 2 right here. So to do that, actually for the cosmological constant case, provided the scale factor right here, I am required a large value of the cosmological. I in fact required a large value of the cosmological constant lambda. And because of that, for that reason, it turned out that instead of becoming 0, it would make the kinetic density become large for late times, in contrast with the matter and baryonic energy, well, content counterparts. So that's that. Not sure if I failed to mention that, but in any case, that could actually also be seen in my code. My code's actually part of my code for this actually. There's a step in which requires the minimum cosmological constant needed to make capital X positive. So and it turns out when I provide I plug in W is equal to -1, I would require that large amount of cosmological constant. So for that reason, when at late times H becomes a constant, rho becomes a constant, we'd get a large value of the kinetic density X, in contrast with the W equals 1/3 and W equals 0 cases. Yeah, so let me just check the thesis for quick. I should mention that in the thesis.
So if I may rephrase, is there any reason why X and rho?
So it's right here.
Okay.
Yeah, so in the thesis, it's, let me share it. Yeah, I've mentioned it right here. Yeah, so we're looking at section 4.2.6 of my thesis. For W is equal to -1, I've used a lambda, which is in units of the energy density I'm using, 3081, compared to the lambda equals 21, which I have used for the W equals 0 and W is equal to 1 cases. So yeah, so that differentiates the W equals 0 and W equals 1/3 cases compared to the W equals -1 case.
So they are different conditions that you cannot overlap the figures because they come from different conditions.
So there are different choices of lambda, right?
Yeah, different choices of lambda. So I'm not sure they all come from the same A. So
or
but
probably
well,
in the figure you should add the lambda as well, because it assumes in the figure that everything else is the same except for the W's.
Yeah. Yes. Okay. Thanks, ma'am. Yeah, I do that. I should do that.
Yeah, but don't the 3 W's correspond to different eras in the evolution of the universe?
So, sorry, sir.
Yeah, the 3 W's, don't they correspond to different eras in
Yeah.
evolution of the universe?
No, not necessarily to the different
so you're
era.
actually comparing this at different times, probably?
Not necessarily with the different eras. So the choice of W basically, well, there's a limited choice here. 1/3 0 and -1, as you can see, stems basically from the fluid components that we understand. So it just turned out that in lambda CDM theory, the history of the universe could be described into different eras, a radiation era, matter era, and a dark energy era. Yeah. So, however, in the kinetic gravity braiding context that I'm working with in this thesis, what I'm showing here is that this if this observable scale factor here provided this, then it would be possible to always connect that with kinetic gravity braiding, even with just one cosmic fluid. So, for example, you'd basically have the same expansion history, provided that your scalar field would have this dark energy equational state. For example, the red line for W equals 1/3, the blue dashed line for W is equal to 0, and then the black dash dot line for W is equal to -1. So in the kinetic gravity braiding context, the W just describes could describe just single cosmic fluid in throughout history. Well, though of course, as Dr. Reyes has mentioned as well, it should be more realistically combination of radiation and matter components. So definitely, that should be a promising problem as well.
Okay. Okay. So this is in another part in chapter 5. Your results is that you have the even parity master equations. Could you then conclude that the scalar field should also have even parity scalar field?
Yes, yes. Thank you for the question. So let me just go to that part of the thesis.
Because there is in the beginning you did not assume any geometry or symmetry for the scalar field, right?
The only assumption for the scalar field is that it's a function of R only, the background scalar field. But in general, the perturbation of the scalar field, on the other hand, could depend on T r theta phi. So it could depend on the space-time coordinates. It should depend on the space-time coordinates in general if it's available. Well, if it's a dynamical field. So I think I should what I could show here is well, for example, this so the expansion of the parts of the scalar field equation which contains the potential K of the kinetic gravity braiding would lead to equation 5.68 right here. So there's that. So you'd see here that the small psi in this equation, of course, it always comes in contractions with the background scalar field. A small psi has dependence on the depends on the space-time coordinates T r theta phi. Yeah, so it only turned out, so that result actually followed from this. It only turned out that the perturbation equation for the scalar field would be yeah, so yeah, am I still not sure what
there is time lag in the PDF. Okay, it's now shown.
I'm not sure what happened.
And now it's okay.
It's showing now equation 5.7 and 5.71.
Yes, thanks. So sorry about that. Not sure what happened with the internet. Yeah, so the scalar field equation would, for the scalar perturbation psi, would actually turn out to be it would turn out to actually be possible to write it down as 5.71. And this one is a linear, this is the first order linear differential equation in the derivative in the radial coordinate r. And you see here that there's no constraint on the other variables of the other coordinate variables describing the evolution of the scalar field. So in general, the result described in the even parity perturbation, the time dependence of the scalar field actually enters through the dependence of this Q. So in equation 5.82, so that's the scalar hair modification to the perturbation. So that should contaminate the even parity perturbation. The time dependence of the scalar field enters as a dependence of this Q in the frequency variable omega. So if there's no time dependence at all, then this Q would actually just be a constant.
So Reg, I think the question is, since it's a scalar perturbation, would you have expected its perturbation to show up in the odd parity sector? Because it's in the even parity sector, right? So
yeah. So the result actually comes from well, I should show this. The perturbation of the full metric field equation is shown here, equation 5.79. And yeah, we see here the first term is just the linearized Einstein equation in GR. We have a second term, K of X naught, so that is for self. Black hole is just a constant. And then we have the metric perturbation, small h. And then the basically all of the scalar field terms in this equation just reduce to this third term in the left-hand side. They just simplify to this third term in the right-hand side. And the notable thing to observe here is that this is only, in fact, an RR component correction to the metric, to the linearized Einstein equation. So the RR component of the perturbations does not have it does not have an odd parity component. And so for this reason, we should expect that the odd parity mode of the black hole perturbations would be unmodified. So I have an extra slide here actually showing the results for the odd parity perturbation. So let me go back to the presentation. So these are actually the results for the odd parity perturbation. So by just following the steps done in GR, then would end up with this following master equation for the odd parity perturbations. That is well known as the Reggie-Wheeler equation in GR. So it's given by that, and it's I should say that this is way simpler compared to the Zerilli equation for the even parity mode. Yeah, so we should expect based on equation 5.79 that there should be no correction to the odd parity modes of the gravitational perturbations, but I have still shown this for completeness.
Okay, thank you. Dr. Galapon, do you have additional questions?
Yes, I have. Wait, I have a problem with my... Okay, please go ahead. I'll ask later. I have a problem here.
Okay, I'm sorry I got disconnected. So the equation, the questions in the chat are first. Are there questions from the panel members, the other panel members, Dr. Reyes, Dr. Esguerra?
No more.
No more.
I have no more questions.
Okay, there were 3 questions, but now they got erased from my
Okay, maybe I can read them. I still see the questions.
we can ask
Okay, so
Adrian Villanueva. That was
yes,
the first.
Adrian. Can we hear Adrian, or do I just read it? Okay, let me just read
I
it.
think you can just read it.
Okay. How would the scalar field affect a theoretical waveform in terms of its phase and amplitude? In short, how can we maybe see scalar field imprints in observing gravitational waves?
Yes, thanks. That is indeed a very important question. But yeah, so to answer that with that, well, I would have to solve explicitly the Rayleigh equation. Although I'd have to mention that even if I have many experience with that, doing that in GR, not actually quite sure yet what would be the result when I finally incorporate the scalar field perturbation shown here. So in this slide 37, and for one, the important step actually is to first provide what Q is as a function of the frequency. So that Q of omega is the residue from the scalar field, and it turns out that for the this is an important result, and could actually signal something that is something that is very, very non-trivial. It's this Q of omega is actually an arbitrary function in this effective field source term. So it's actually an integration constant stemming from the scalar field equation. So there is an unrestricted time dependence of the scalar field perturbation. So the answer to the question actually depends on first specifying Q of omega is, but then the question would turn to how would we select any physical Q of omega compared to other choices of Q of omega, and yeah, that's it.
So Reggie,
so then I'm not sure. Yeah,
let me just rephrase it a bit, because I think Adrian is asking a far more general question. So the perturbation equations that you present here, they wouldn't be valid for a binary black hole that's governed by two large black holes that's governed by, say, KGB theory, for example. So what would you physically expect, or what might physically happen if you had a binary black hole that's governed instead by KGB theory instead of GR? Way of answering Adrian's question physically and in more generality than what your equations can possibly provide at this point.
Yeah, so the main result actually in there, so we found that the black hole perturbations for self black holes, the even parity modes would be contaminated with scalar hair. So we're not exactly going to get the same gravitational wave signals as in GR. So for in the binary black hole context, and we know that we know that the late time signal of the gravitational wave forms in general is contaminated by quasi-normal modes. And this is again the regime where the black hole perturbation theory should work. So then it means that in the gravitational wave astronomy context, we should be able to use the ring down signal to constrain the effective scalar field source term if there is. Yeah. Thanks.
Okay. The next question is from Gabriel Dizon. Dr. Esguerra, could you please read?
Okay. Aside from scalar hair in black holes, What cosmological signatures do we expect for scalar tensor theories?
Yeah, thanks. So of course the scalar tensor theories would predict a deviation of the local solutions of a gravitational theory. So at the for cosmological distances, because we now have a scalar field, so the cosmological signatures that we expect is of course the now a dynamical dark energy field, and of course then we won't have to answer the problem now. Why do we get we may not necessarily answer the problem why should the vacuum expectation value of the cosmological constant be different from the one predicted by the observed late time expansion. Because the late time expansion would now be sourced by the dark energy field, which is the scalar field, and it could evolve in ways much more different compared to just assigning a lambda as in lambda CDM theory. So instead of just having lambda, we'd have a dynamical scalar field, which could, for example, mean dynamical dark energy field. If the speed of propagation of the dark energy field should be less than 1, then we would observe a clustering of dark energy. So that's one example of a cosmological observable that we expect in scalar tensor theory.
Third question.
Third question from Victor Ying, Charo, and Rap. Okay. I was wondering whether or not you have a problem with the hairy solution when big X approaches 0 for the cubic Galilean case.
Yeah, so that is an important question, and yeah, there's a problem. So not necessarily a problem, but if you wish for your theory to be compatible with Lorentz invariance, then that is indeed going to be a problem. So because as you'd see here, and the theory function would actually have to depend on inverse functions of the kinetic density x. Then as kinetic density x approaches 0, one would observe that the Galilean parts of the theory action or the stress energy to blow up, signaling that your theory would not in general may not in general accept the existence of a Minkowski spacetime or rather a Minkowski vacuum. So this, if your theory potential turns out to depend on inverse functions of the kinetic density, then these theories would not be compatible with Lorentz invariance. So that's for this hairy black hole. But for the stealth black holes, these are still hairy black holes. The potentials don't have to depend on inverse functions of the kinetic density. So the only constraint to the potentials is that the first derivative of the potentials k and g evaluated on the background kinetic density x naught would vanish. That's the only constraint right there. So the general problem that we could expect for in the limit x is equal to 0 is that if the theory potential depends on inverse functions of the kinetic density, then we would have a violation of Lorentz invariance in the theory.
Okay, another question from
question. The last question. Okay, did you see it? The one from Jezreel Castillo?
Yes, I see it.
In the gravitational perturbation part, since the monopole and dipole modes cannot be gauged away, then should we expect monopole or dipole radiation?
Yeah, thanks. Yes, so the answer is yes. So this term, I'm very sure that these are not gauge modes. I mean, I've spent I think around a week or two just trying to gauge this away, and then coming up with a general condition for just removing possible gauge modes of the perturbations. So that is in one of my mathematic codes uploaded in my website as well. Yeah, so these are not gauge modes, so we should expect in general in scalar tensor theories that there could be monopole and dipolar radiation. And I should mention for the audience that this is important, in fact, because in the general theory of relativity, black hole perturbations would not have monopolar and dipolar radiation. So in scalar tensor theory, we are witnessing here indeed a significant deviation from GR, one in which there's a monopolar and dipolar radiation that we should expect in our gravitational wave signal.
So I think that question is related to Adrian's question earlier about the waveforms, scalar field imprints in observable gravitational waves.
Yeah. Yeah, there's so there's going to be a monopolar and dipolar radiation, and yes. So while this comes from black hole perturbations, we should we could expect this as well for in general for the waveforms for black hole binaries. Should the theory of gravity be a scalar tensor theory? Yes.
Dr. Galapon, your question?
Oh, yes. So in page of your thesis, in page 29 of your thesis.
Yes, sir.
Yeah, page 29 of your thesis. So there are three possible branches of solutions. And then you ended up with a conclusion that only the first branch is acceptable, and in which the background kinetic density is covariantly constant. So what does that mean? Is that the only possible solution? So what if it is not covariantly constant? So there is no non-covariantly constant solution.
Yeah, thanks, sir. Yeah, so to determine the possibility of self solutions in kinetic gravity braiding, what we actually did there is to impose that the space-time be maximally symmetric. So this basically just means that the Riemann tensor of the space-time be metric minus metric multiplied to a constant. And the constant in this case, we could just name it anything. And by doing that, we'd end up with the following condition. So these are the there are three branches indeed. So the main point of this part of the thesis is, in fact, that the only branch which would not signal a diverging scalar field, or rather an unphysical one, would be the first branch, in which the conditions for the potentials are given by equation 3.16. So let me show it. So yeah, so that's the only physical condition that we have narrowed down. So the other branches of the equation is this. So we have the second branch given by equation 3.17. In contrast with the first branch, see that this requires capital X, or rather the kinetic density of the scalar field, to be zero. And that would, of course, for non-singular theory potentials, that would, of course, mean that the stress energy tensor, the scalar field would vanish, or that the theory would just the background field equations would simply become just GR. There's a third branch in which one given by equation 3.18, in which 1 over x should be equal to 0. Again, this is another unphysical unphysical branch, because this would then imply that the for 1 over x to be 0, the kinetic density of the scalar field should be infinite. So we've basically just what we've basically the main result here is that there's just one physical branch, and this is the branch that we have narrowed down to lead to self-black hole in shift symmetric kinetic gravity braiding, and that physical branch is given by 3.16. Yeah, and so that I could just clarify, by covariantly constant, it means that when using the four-dimensional picture, and then we then a covariant constant would not depend on either one of the space-time coordinates in any coordinate system.
Okay, thank you.
Thanks.
Okay, so just last here in this page 29. I'm trying to understand, when I was reading your thesis, what do you mean by a massive minimally coupled scalar field?
Yeah, thanks. Page 29.
Right above 3.3. What do you mean by a massive minimally coupled scalar field? Because there are non-minimally coupled scalar fields. So how do you distinguish between the two?
Yeah, thanks. So we are actually familiar. So before this, we've actually have already determined that the kinetic density of the scalar field must be constant. So it means that K and G evaluated as the background should have to be a constant. And so what I mean with this is that when comparing this Lagrangian right here with the Lagrangian that we are most likely everyone is familiar with in scalar tensor theory, this would, well, I'm sorry about this, but this would not exactly actually be a corresponding to a massive minimally coupled scalar field Lagrangian. So I'll check for accuracy. But for a massive minimally coupled scalar field, we would expect that there be this Lagrangian L would contain a term that is quadratic in the scalar field phi. So because by then, when after performing the Euler-Lagrange equations, or just vary the field equations with respect to phi, would get a mass term, which comes basically from the part of the Lagrangian quadratic in the scalar field. Yeah, sorry about that. But then the more accurate statement here would actually be, so this would be the Lagrangian for a scalar, for a massless scalar field with a source term with a constant scalar charge. So the scalar charge is correct. G sub x over k sub x. So I should remove the massive. Should actually remove the massive. So this for some would call this a tadpole term. This would after performing the partial L partial phi part of the Euler-Lagrange equation, that would lead to a source term, constant source term given by this G sub x over k sub x constant.
I think Dr. Villagonzalo is just asking, what is minimal coupling in?
Yes,
what do you mean by minimal coupling?
Yeah. So for minimal coupling, it means that the scalar field couples with the metric only through its kinetic density. So the important um, not sure if I have any question. Yeah, I'll go back to the slides. I think I have an extra slide for that. Yeah, so this is the theory for the inflaton. So this one is a minimally coupled scalar field to the gravitational background. Typically, this theory is used for describing the inflationary era of cosmic history. The first part is where we see that the kinetic density part is not actually just dependent on the scalar field phi, but this actually contains a dependence on the metric. And so the more accurate way, the more precise way of writing that is given by this one. Where's the definition? So this last equation right here. So this is what we mean by minimal coupling. So you have
Reggie, how do I make that non-minimally coupled? So the simple inflaton case that you, because I think Dr. Villagonzalo is just asking a distinction. So take the very simple example. That's an example of a minimally coupled scalar. So what is an example? How do I make that non-minimally coupled?
Yeah. So one way to do that is to for example, related to the question of Dr. Galapon earlier, when we plug in an arbitrary function f of the scalar field in front of the Ricci scalar in this action, and then in that case, we would have a non-minimal coupling between the tensor GAB and then the scalar field. So by minimal coupling, that simply assumes that every time we see a derivative of the scalar field, it would come in this combination partial phi squared given by this last equation right here, in which couples to the metric always in this particular way. So if you want to break theory which has non-minimal coupling, what you could do is to add terms in which there is in general a dependence on a different dependence between the scalar field and then the metric tensor.
Okay. Are there other questions from the panel? There are no more questions from the chat. The panel, Dr. Reyes, Dr. Esguerra, Dr. Galapon.
I'm good.
More questions? Thank you.
I'm good. I'm good. I'm good.
Okay, so let us thank Reginald, Christian, Bernardo for this dissertation presentation.
Thank you, Jane.
Thank you very much as well.
Okay. Yeah, may I request? Okay, thank you.
So
yeah, I think we are about to discuss. Maybe we can remove this from YouTube Live.
So I think
yeah, the panel is about to discuss. So you should remove this from YouTube Live.
So I think we probably have to start our new. We probably have to start our new.
You should start a new meeting.
Okay, maybe we just start a new meeting.
Yes, please, yes. I think it's better.
Let's stop recording.
Dr. Garcia is asking for a picture. How can we do a group picture where we have everybody there?
You stop the screen sharing so we get the grid.
Not actually sure.
You stop the screen sharing first.
You have to stop.
Yeah. So I'm going to stop this. Yeah.
And how can we do as a group where we have all our pictures there? Who knows?
We might not be able to fit because there are so many of us.
Oh, the gallery view will adjust it.
We have
will
2
adjust the
pages.
size.
So we can start with the first page. Okay. Smile, everyone.
You can do it.
So those who are not
all right.
magpakita naman kayong lahat. Nahihiya naman kayo. Alam naman namin na wala kayong ligo.
There's just a lot of photos.
Kakagising lang ng madami din dyan eh.
Okay. No.
Who has taken the
Dr. Garcia is topless daw, so he will not show himself. Thank you for the information, Director Garcia.
Okay, we have a good photo. Smile. All right.
And there's another one, I think. Second. Where is everyone on the second set?
Okay, I got one for each page, but you can more.
Okay.
Ayan, I think there's
Thank you.
I've also designated someone from the group to take photos.
Great.
Right. So thank you very much. So that concludes the defense, the public part of the defense. I think by tradition, the panel will have to meet and discuss privately. I mean, lest of course we want to make public all the bad things we will say about Reggie behind his back. So thank you very much for attending. This was a first. There will be several more PhD dissertation defenses in the next couple of weeks. Accordingly, pwede daw gumawa ng breakout room. I have no idea how that's done. So I think, yeah, for simplicity, we'll probably just start a new. So panelists, can I request that you remain online so we can discuss. For the rest, thank you again for attending. We look forward to your attendance in the next dissertation defenses as well. So thank you very much. I'll ask our host, and thank you again, Reggie. We will get back to you in a few minutes, a couple of minutes.
Yeah, thanks.
We'll send you the link of the new meeting. So maraming salamat po sa lahat ng mga nag-attend. Host, paki-end ng meeting na. We'll start our new meeting.
I'm going to end the meeting. So thank you everyone. So I'm ending the meeting right now.
Thank you very much.
How do we get the link?
I'll send it.
Okay.
Okay.